Hello, can you hear me? Okay, nice. I guess I'll just start. I think people just didn't recover from hangover. Okay, cool. This is recording. So I guess like the main thing that I'm gonna second part of the course, which is starting from op amps. So these are the basic things for op amps, which like we basically know op amps, when you solve op amp questions, you have to assume they're ideal and you have to use nodal analysis, and then you just solve for the values that are known. And when you assume the op amp to be ideal, there are two golden rules that you have to follow. The first one is this one, which the current that goes into the both inputs are 0. And the second one is this one, which is called virtual ground, where all the voltage at both inputs are the same. So, for example, this is a simple example that we can follow. So I'm gonna go through like this very quickly without actually calculating the real values, but like just writing the working out like would help. So let me see. Let's start with this one. Ooh, do I have it? Okay, so this point is V1, this is V2, and yeah, that's pretty much about it. So I'm just gonna show, oops, I don't have any more. Okay, current here is 0, current here is 0, and then we have our V out here, and this is the same as V2. This is actually V2. So if we do like node analysis, this is also our V1. We get, let's mark all the currents like that way. And then we get 9 minus V1 over 4K. It's equal to, since there's no current going through this way, like it's equal to this current that goes down. So equal to V1 over 8 kilo ohms. And actually you just work out V1 like based on that. And then you get an equation and you get V1. And then the second equation would be, let's mark the current. So say this one and this one like that. So V2 over 2K plus V2 minus V out over 5K will be equal to 0. And since V1 is equal to V2, you can just solve for VO and then you get the answer. Yeah, so like it's a pretty like big circuit that you see, but it's actually pretty simple to solve. You just need two equations. You have two unknowns. You get the first unknown from the first one, and then you just solve for V out. This is another example, which like it's an op amp circuit with a capacitor, and it also like adds this Vs equal to 10 the step input. I don't know if you guys remember that the step input is like something like that. So after 0 it is 1. So before 0 it is 0, of course. So for example, for this one, you can solve it for t less than 0 or t greater than 0. So if you solve it for t greater than 0, the capacitor in DC, it's open circuit. So I don't know what it's asking me to find VT. Okay. Let's do first t less than 0. And then we get basically the same circuit. And this is V 0 minus. This is 100K, this is 20K, 20K, then 100K. So Vs is like input voltage has been 0 for a long time, becomes 10 volts at t equals to 0. Let me see if I ever solve this question. Clearly I didn't. Okay. I lost it. Okay. So this one, basically, if I just assume, I'm not too sure if it asks me for the total or not. This t equal to 0, this is actually 0, because it's like 10 times 0 ut. So there's not much to solve, because like you wouldn't get like anything at the output. So at t greater than 0, so this is V equal to 0 volts. And then if I copy and paste the same circuit to this side, this is 10 volts. So we get infinity. So this is our V1, this is our V2. And for example, the currents are like these and that. So the equation would be 10 minus V1 over 100K. It's equal to you can assume that all the current goes through like that. So this is directly, this node is directly V infinity. So equal to V1 minus V infinity over 100K plus 20K. And then V2 is just, V2 is just 0 because it's attached to ground. And V1 is equal to V2, so they're both 0. So what you get in here is 10 over 100K equal to V1 minus V infinity over 120K. Oops, this is 0. And then you solve for that, and then you chuck in the equation of the VT of the capacitor, which I think it was V infinity plus like V0 plus V infinity e2 minus t over tau. Yeah, something like that. I don't think you really need to do this, to be honest. I think you just need this equation to find VT, and that's it. Okay, cool. This example, I'll leave it to you guys to solve it, because I don't want to do like all the op-amp questions. So, okay, this is like a summary of the op-amp types. So sometimes when you if you remember them, it'll save you time, especially for the inverting amplifier or the non-inverting amplifier, which are the most commonly used. So like once you see this circuit, you don't need to do a nodal analysis, and you can just directly use this formula to get the gain or like the output value that you have. But if it's like a more complicated circuit, like the ones we saw before, then it's probably good to do like the whole nodal analysis. So basically for the AC circuits, we have different forms to write it down. So this is the time domain, the Cartesian form, the phasor domain, and the exponential form. So we use mostly the phasor domain to like write in the to solve like the circuits. And for phasor diagram, like in case they ask you in the final to draw, the document I'll send it at the end of the whole course, so don't worry about it. So I'll send it, I'll send one that is like clear with all the solutions, and probably one with the scraps like that I write, yeah. So for the phasor diagram, this is the leading direction and that is the lagging direction. I'll probably leave you guys to read it like afterwards. But if you write it, like if you ever draw it, you have to draw it like this is the magnitude, which is like your A, and then your degree, which is like respect to the x-axis. So you have like here 45 degrees. And then very important things that you guys have to remember, and this is a very rookie mistake, is that phasor or polar form can only take positive amplitude and cosines. So it means that whenever you have an A sine 2t plus 30 degrees, it doesn't mean that it's A like angle 30 degrees. You have to like change the sign into cosine and then start like analyzing your circuit. So to change it, you can either add or subtract 90 degrees, and then you get 110 degrees. And then this A angle 110 degrees, it's actually the real value that you have for your phasor form. And another one, for example, if you have minus A and then you have cosine of 30, your amplitude is actually negative. So to swap your amplitude to negative to positive, you have to plus minus 180. So you get a positive one, which is like angle 100 minus 150. So yeah, this is like the lecture slides that you guys would have for your imaginary numbers and like the properties. You don't really need this because you'll have the calculator, but just in case, it's good to know like the yellowy thing, or like 1 minus j is actually minus j. Okay, cool. So I'll probably skip this because this is the resistor capacitor impedance, which is 1 over j omega c. Inductor is j omega L, and these are the formulas. So let's start with like the example. Let's see. So what is it asking me? Yeah, like I don't have the question, but like it's asking me to solve for V out. So for these, I have my omega equals to 4, which is this number. And then the first thing that you need to do is that you change everything into impedance form. So for example, these two things, I need to change it to impedances. So for example, 10 megafarad would become 1 minus j omega c, which is, how much is that? J times 4 times 10 to the minus 3. minus J250 ohms. And then the 5 would go to J omega L, which is J omega L J20. And then the output is just basically, like, this is a very simple, how can I say, voltage division. So you can see that these two impedances are in parallel. So what you do is that you just do minus J250 in parallel with J20. And then this value, like Z total, let's say, or like, nah, let's put it as like Z1. And then you just do a voltage division, which is V out equals to Z1 over Z1 plus 60 ohms multiplied by your V in. And in this case, what is your V in? Your V in is 20 angle of minus 15. And I think the final value of this one is J 60 times 20. I got 6.81 angle of 55.1. And that is your V out. So pretty simple one. And this is pretty much the same. So you have, it doesn't tell you the omega, does it tell you? Yeah, I'll give you guys the omega because I think I just like cut out this question. So omega is equal to 20 and the 1 microfarad would go to 1 minus J omega C, which is minus 50. And then the 8 would go to ZL J omega L, which is 160. It's just the same like questions like over and over again, to be honest. So what you have in here is that you have 160 in parallel with 200. Oh, sorry. Plus in series with 200. And then all these will be in parallel with the minus 50J. And then that will give you 56.1, angle of 82. And then you find your Z in, and that will be this. And this is your Z in. So this is what you got for 56.1 minus 80.2. And you get simply as resistances in series, which is minus 50J plus 100, plus your 56.1. And I think that gives you this. And always put the symbols in, because otherwise, like, you just get 1 mark subtracted. Because I think a lot of people like got marks subtracted because they didn't put the units in. So be careful of that. Okay, let's see this one. Use source transformation to find Ix in a circuit. This is a longer one. So I'll probably quickly like go through these. So I'll first do the source transformation of these, which is gives me a current. So remember that if I have plus minus, the current will go up. If I have like minus plus, the current will go down. and I would have impedance in parallel, and then another one in parallel, and then this one, and then my current at the output. 590. This 4 minus J3. This is minus J2. 6. And this is 2 plus J4. And the current, this current is this voltage over 2 plus J4, which it gives me 13.4, and then minus 63.4. And then I do, like, I combine this in parallel, and then I'll get, and then I do again the source transformation. So let's see, can I just copy this? Oops, make it small. Okay. When I combine these in parallel, I'll get, yeah, let's say Z, because like Z is actually equal to 12 over 5 minus 1 over 5J. And then you do again a source transformation on this. You get let's say 40. Yeah. So this one actually become your Z plus minus 2J, because you had that minus 2J. So when you source transform it, like the Z will go to here, which will become in series with this capacitor. So, and this voltage would be 40.2 minus 26.5, which is your I times R. And then your R is actually your Z. And then I think at the end, what you have is this, oops, this big current. You get an impedance in here, and you get another one that is your 4 minus J3. So you just do a current division and you get your final answer. Because I think Ix is this. For that, no jokes. Ix is this. Okay, cool. Okay, so I think a lot of people put it like questions about Thevenin and Norton. I think the hardest part is like when you have to find your equivalent impedance when you have like a dependent source, because when you have whenever you have a dependent source, you need to connect a 1 volt source or like a 1 amp current source to find your equivalent resistance. So in this case, if you have, let's say we put in 1 volt one, we have this plus minus, and I have 1 volt. So what I can do is like, I can first do a source transformation on this one. So it will become plus minus, and then 1 volt. This is 10 minus J2, J40. And my voltage would just be 0.2 V naught times J40. Yeah, 0.2 times J40. Which is AJ V naught. And then we just simply do a mesh analysis, which gives me, yeah, let's do it in the other direction. This one. That'll just be, I have -1 plus 10I minus V naught. It's actually my V naught's here, right? V naught minus V naught plus J40I plus 0.2. Plus AJ V naught equals to 0. And this gives me a, okay, so V naught, we can find it as minus J2 times I. So it will give me at the end I equals to minus 15, 10 plus J42. And the rest is just algebra. So you can just like solve for like the unknowns and everything, and substitute and everything. Do I want to do this? Let's see the time. Okay, 9:41. We still have plenty of time. Okay, cool. So it says use superposition to find Ix and Vx. Why do you need to use superposition? Because in this example, you have two sources. And when you have two sources, like especially in the second example, you have two sources with different omegas. So it means that you have to solve it like separately with one source on and the other one off. So, and then you add it up at the very end. So I guess I'll just do B because A is pretty much the same. So B. So we have 50 sine of 2t, and to convert it to cosine, that will become 50 angle of minus 90. Because you go to like 50 cosine of 2t minus 90. Yeah. And then my omega in this case is 2. So let's put like omega 1 is equal to 2. And then my 50 microfarad would become minus J10. So the first one, say I call it Vx prime. I'll have this circuit. And then my impedance. And then this is off, yeah, in this case. So I get my J10. Oops. My J10, my 20, and then 50, angle of minus 90. So a very simple thing to do when you have these kind of questions is that you just have two values that are in parallel. You just solve for that parallel, which would give you like a circuit like that. An impedance in here. This is still 20. And then you just do a voltage division. So I think this will give you 4 minus J8. And then your Vx prime, in this case, Vx prime, would be just 4 minus J8 over 4 minus J8 plus 20 times your 50 angle of minus 90. Okay, so let's make space for the other one. So say Vx prime prime would be 20, 20. My impedance, and then my current. And then in this case, be careful, because like this is 12 angle of 10, but actually my omega 2 right now, it's 6. So you have to recalculate this impedance, and then my new impedance would be, say, minus 10 over 8j. 10 over 3, sorry. Oops. And then this is still 20 and 20. So this is pretty simple. You have 3 impedances in parallel. You solve for them. You get 1 impedance. You get your current source. And then you just solve for the Vx that is right here. Vx double prime, which is just the current over your impedance. Okay, cool. Do you want me to go through this one? Or like, do you want me to continue with like the other ones? Okay, so this is a AC op-amp question. So it looks like super scary too, but like if you actually use the op-amp rules, like it's pretty easy. So for example, I'll just first put all the voltages. So this is 0 volts, and this is also 0 volts, and this is 0 volt, and then 0 volts. So then I label the currents. I have current going in, current going out. I should label it better. Current going out, current going out. And we know that the current in here is equal to 0, and the current that goes through is also equal to 0. So in this question, we have a big omega, which is omega equals to 10 to the 3. And then we have a Vs, which is equal to 12 angle of minus 60. And then let's change the impedances. So 0.1 microfarad would go to minus J10. And then 0.2 microfarad will go to minus J5. Okay, because 5,000. And then if we just use KCL, we can see that let's label this I1, this is I2, this I3. So I1, it's equal to Vs minus 0 over minus 10K. And then I2, it's equal to 0 minus V out, because it goes all the way here. Oops, all the way here. And this is your V out. Over 50. 50K. And then my I3 is just gonna be, because my I3 will travel like that. So you can simply put 0 minus V out over 20K plus 10K plus minus 5J. Okay. And then you have 3 equations. You have 1, 2, 3 unknowns. And then you can just simply solve like I1 from these. Then you get like VR with those 2 equations, and you can just like solve it out. So you just need like 3 simple equations, and then you get it. So it's more like algebra. As long as you get the equations right, if you don't get the algebra wrong, you get it right. Okay, cool. So this is already solved. But basically it's the same. So you have like two impedances, and you have like all these currents going in. This V out, this one is your V out. So like this one is also your V out. So when you formulate your say your equations, you just need to take into account that you use node analysis to do it, and then the working out is already like at the very beginning. So it asks you also to calculate the input impedance, and then the input impedance you need to solve for your IS and then divide it. So input impedance would be your VS over your IS. So to do that, you need to find your IS. Okay. Let's see. So this is AC power. So for the power, you have different, like so many equations of power. So for instantaneous power, which power at any time, you get these kind of equations, and you can see it on your lecture slides. So they're all in the time domain, and the total power is this long thing. For the average power, there's something to remember. When you have your theta V equals your theta I, which is your voltage and your current are in phase, it means that you have a resistor. So your average power would just be this, like the modulus of voltage over 2 times R. But when you have them shifted by 90 degrees, like plus or minus 90 degrees, it means that you have a capacitor or inductor in your circuit, and the average power for any inductor and capacitor is always 0. So you get just 0. So one hard thing that you guys have is the maximum average power transfer. So you have two cases. The first case is that when your Z dividend is not pure real. So when your ZL, it is imaginary. You like the question on the final will probably label it as Z or label it as R. Or sometimes it will just like ask you to calculate it and then let you find out by yourself. But when it's impedance, the actual ZL to get a maximum power transfer, it needs to be the conjugate of Z dividend. So I'll let you guys know that ZL equals to Z dividend star. This star actually means conjugate. So the maximum power is this formula. And then your R dividend on this question is the real part of your Z dividend. So in case 2, when Z7 is pure real, when you have a resistor load RL, your Pmax would have a different equation, which is this. And then your RL for maximum power transfer is the modulus of your Z7. So you have to do the square and then the real part, the imaginary part squared, and then the root of that. And then effective or RMS value, these values are assuming if they're a sine or cosine, which is like the main case that you guys are gonna encounter. So I don't think you need to worry too much about it. It is not like a big chunk of the course that you need to consider. So just like remember that this is actually like RMS values of sines and cosines are just the actual value divided by square root of 2. Okay, let's do examples of maximum power transfer. So I put one example with imaginary load and another one with real load. So let's solve the imaginary one. So first thing first, I need to calculate my Z dividend. So my Z dividend would be these. I short circuit my input source, my capacitor, and then my Z dividend. What is my R1? This is 100, this is J100, this is minus J100, and this is 100. So maximum power for impedance load is ZL equals to Z dividend conjugate. So your Z dividend in this case is just 100 in parallel with J100, and then minus your J100, and then in parallel with the final 100, which is, I don't know, never calculated the value. $100 plus J. Hundreds. Okay, got 74.54 minus 26.57. Or in Cartesian form, it is actually 200 over 3 minus 100 over 3. So it means that my ZL needs to be 200 over 3 plus 100 over 3J. So we got that. And then we need to find the maximum power. So we need to solve for V Thevenin right now. So for my V Thevenin, just copy paste these. Adding my source, which is 100. Angle of 0. And then now this is V Thevenin plus minus. So let's label this as V1, this as V2, and the currents like that. You can just label, you can just put the currents the direction you want. Like as long as you think like it's the most comfortable way for you to derive the equations. Because at the end, no matter what direction you put it, you get the same answer. And I know that IMA tend to like ask you guys to put the minus and like plus and minus on all the components, but I don't do it because like what I simply see, like it's just like for any impedance, I just put a plus in my equation. And then when I see like a source, for example, if my current goes through like that, it enters the negative terminal, I just put it negative. If it enters the positive terminal, I just put it positive. So that's what I do in like to avoid confusion, because sometimes when you have like too many plus minus in your circuit, you just get confused. And eventually you get the same answer. So like you don't really need to put the plus minus, but unless like you really like it putting it in, or like that's totally fine. So let's solve for the first part, which is 100 minus V1 over 100 equals to V1 minus V2 over J100. And then this is plus V1 over J100. So the KCL right in here. And then the second KCL would give me V1 minus V2 over minus J100 equals to V200. So this current in right here is actually equals to 0 because this is open circuit, yeah? So there is no current going through. So you have two equations, two unknowns, you solve for the unknown, and then you get V1 and V2. And in this case, your V2 is actually your V Thevenin, yeah, because they're the same node in here. So after you get that V Thevenin, you just apply the formula of P max equals to V Thevenin. Oh, let me check. V Thevenin module squared over a RTH. So the RTH in this case is your 200/3, the real part of your ZL. And then your V Thevenin is whatever you get from here, but only the modulus. So say if you get like, I don't know, 30 angle of minus 40, you just need this 30 squared. You don't need to care about the angle. Okay, this is just only an example. So let's now go through with load resistance. So in here we can see we actually have a dependent source, but this circuit is actually a little bit special because like if you can see on the left hand side you have like a closed loop, and then your I node would keep looping on this side. So it means that your I node would always be 30 millivolts over 500 ohms, which it gives you 0.06 milliamps angle of 0. And this is, and like actually like if your I node keeps looping on this side, like it's actually like a constant value. So your I node, if your I node is a constant value that you can already calculate it, it means that this dependent source 20 I node, you just multiply it and you get, what is 20? Oh, okay, 1.2 milliamps. So it means that this dependent source will actually become an independent source, that you can treat it as an independent source, because like you already have a constant value of I naught. So like every time when you put, like when you multiply it by 20, it's going to be the same. So in this case, to find R Thevenin, you don't need to connect like the independent 1 volt or 1 amp. You can just treat it as a independent source. So if I'm calculating for my R Thevenin or Z Thevenin, let's say, I short circuit my left hand side. So if I short circuit these like that, so if I short circuit this side, like the left hand side, it actually gone. Like you short circuited like a resistance, so it's gone. You only have the right hand side, and we calculated this to be 1.2 milliamps. This is 4K. This is my J3, J1, and then your Thevenin. So this is my 4.8. We do a source transformation on this one, and then I'll get a 4.8 volts, and then my Thevenin. And this is my 4K minus J3 and J1. So actually let's rename it because I don't want you guys to get confused. Z Thevenin, Z Thevenin. So my Z Thevenin is actually my 4K minus J3 plus J1. And then for maximum power transfer, this will give me 4K minus J2. So for maximum power transfer, my ZL needs to be, or my RL needs to be my modulus of the R Thevenin that I got. So this is 4,000 squared plus 2 squared, and then root of that, and that will give me 63.28 ohms. And then in question B, question A is asking you to calculate the value of the load resistance, and question B is asking me to calculate the maximum average power transfer. So question B would be, you already have your V Thevenin, like this is your Thevenin circuit if you realize. So you get your R Thevenin here, or you get your Z Thevenin here, and then your V Thevenin here. And then so your V Thevenin is actually just 4.8 volts. And then you have your RL connected in this side. And this would be your VL voltage. So you need to calculate VL, which is voltage division. So RL over RL plus Z Thevenin times your V Thevenin. And that will give you a value. If you substitute like whatever you got in here, and then you actually hold Z Thevenin, and then you V Thevenin, and then maximum power would just be your VL, the modulus squared over your 2 over RL. So yeah, that's it. This document actually includes like digital design, but I think they got rid of it, of the content. So I don't have more examples to go through unless like you guys have anything special that you want me to go through. I think I left one of the questions up there, but I didn't solve. This one. This is a 2014 final question. It's pretty different than I have. Say this is just another op-amp. Like actually this op-amp question is almost exactly the same as one that I solved below, because it also has like a resistor R3 that goes all the way at the top, and it has like this resistance. It's almost exactly the same as, let me check which one, as this one that I solved. So in the final thing that I attached to you guys, I think it's a little bit different from this one and that one, like some of the questions, but it has like all the solutions. So I'll just show you in here. Okay, so as you can see in here, I have an example. In here, I don't have it. But this is the final document that I'll send it to you guys. So there is a different example that we didn't go through today, but all the solutions are down here. So you have 2 inverting amplifiers, one at the bottom, one at the top. So as I said before, either you can just directly use the formula, or if you don't remember the formula, you don't need to panic. You can use KCL to do it. So it's just a little bit longer, but you get the same answer. This is one of the examples we went through today. So 0 volt minus 5 volt, and then you calculate your total. Yeah, this is a repeating one. I want to know if I ever had. Okay, so I also have notes for the first half of the course. I guess you guys are pretty familiar with all the notations and formulas for Ohm's law and Kirchhoff's current law and parallel resistance, blah, blah. These are some examples that we have for example, finding the equivalent resistance. This is some example about nodal analysis or mesh analysis. And at the very end, we have in here the circuit theorems. So I think this is the main thing that everybody struggles with. So circuit theorems, we have superposition, we have source transformation, and we also have Norton's theorem and then Dividend theorem. So for Norton and Dividend, the hardest part is actually to find your R Thevenin or your V Thevenin. But that's like, you can find a way to solve it using anything as long as you can get it. So you can solve it with mesh analysis, nodal analysis, or you can use it solving like with superposition, with source transformation. So that's anything that you can like do to find your R Thevenin. So this is one example where you have to find your R Thevenin with a dependent source. So in here, I added a 1 amp source, and then you guys can see it working out. Don't trust too much on the actual numbers, like just focus on the working out, because I might have like typed the wrong number into a calculator, I don't know, but like, yeah, you can check, like cross check. And the maximum power transfer in DC is this one, V Thevenin squared over 4 times R Thevenin, which is very different to the AC type. The AC type will have 2 cases, but for the DC, we just have this. So this is an example of a source transformation, which also asks you to find the maximum power transfer. You get these kind of questions in your final, actually. Like, you see that's pretty long, but it's actually not that bad. You just need to find like the right way to solve the question, like the quickest way you can. So in here, it actually already told you to use source transformation. So a very obvious part is that you can source transform this one, and then you get these 2 resistances in parallel, and you add the currents and merge it into one current source, and then you just solve for this. Yeah, you can source transform this one again, or you can source transform that one again. And then you just like get a very simple circuit like this. You just have to source transform many times. But like, it is not that hard. It's just like Ohm's law. And then you redraw the circuit, which is like the long part. Okay, so capacitors and RC circuits. Remember that in parallel, capacitors actually add up, and in series, they're actually like treated as in like the reciprocal of it. So time constants, and then we know that this is the formula for the response of the RC circuit. So these are some of the examples that I included. You guys can check it out later. So this is an example with the inductance, and then here we come with the op-amp. So if you have any like specific questions or specific like circuit that you want me to go through, I can do it now. Or otherwise, I'll just send you guys the notes, and hopefully it'll be useful for you guys. And like, good luck to the people who didn't recover from the hangover yesterday night. And I guess they can just get the recording later, and this will be uploaded or send it to via email or something. I don't know. Just check with the ELSOC people. Okay, let me export this. Just stop the sharing. Okay, so final reminder, I will send all the notes through. I don't know how the people who organize it would like to share it, but it's probably via email. But I'll attach it to this chat as well. But I don't think you guys can access the files in the chat if you never join in the chat. So yeah, they'll sort it out. Hey, this actually ended like quicker than I thought. Okay, nice. I'm all done. So thank you for showing up, and I hope this one was useful for you. Bye bye.